Welcome back. In this video, we're going to be talking about expected value. Expected value is kind of a long-term average. So if we were to repeat an experiment infinitely many times, the expected value would be kind of the average over all of those different trials. So as a couple examples, if we were to flip a coin 1,000 times and we wanted to know how many heads we would expect, well, you could probably figure this out without really knowing the math behind it, because we expect every time we flip a coin, we expect that there's a 50% chance that it's heads. So we would expect half of the coins to be heads and half of them to be tails. So we would expect 500 heads in this case. Now, if we were to have flipped the coin just one time, we wouldn't really know what to expect. It could be heads, it could be tails. There's really no good way to guess. But if we do it a bunch of times, then we can kind of make a guess. So in this case, we would expect or guess that we would get 500 heads out of 1,000 flips of a coin. Now, chances are it won't be exactly 500. It could be 499 or 501, but chances are it's going to be pretty close to that. Likewise, if we roll a die 600 times, how many threes would we expect? Well, when we roll a die, we would expect 1 out of every 6 to be a 3, since 1 out of the 6 sides is a 3. So out of those 600 rolls, we would expect 100 to be 3s. So this is expected value, the long-term average. If we were to do something a bunch of times, kind of what do we expect on average in the long run? So let's look at a real-world application. A company sells mattresses online and gives customers a 365-night trial with free shipping and free returns. The company loses $114 if a customer returns the mattress and profits $585 if the customer keeps the mattress. The return rate is 12%. We want to find the expected profit for one mattress. The formula we're going to use here is E of X equals the sum of, and so we write that sum with the Greek letter sigma, x times p. So the x's are the random values, so they're the values that are at random. We don't know which it's going to be. And then p is the probability of that random value occurring. So what we're generally going to do here is draw out a table with the x's and the p's. So the x's, in this case, will be either the loss or the profit that the company makes. So the two different options are either the company loses $114, so that's if the customer returns the mattress, or they profit $585, so that's the other option. Now, the p's, which will go under those, are the probability that each of those happen. So the return rate is 12%, so that goes with the loss of $114. So we put 0.12 under negative $114. So if we know that the return rate is 12%, then that means 88% of the customers don't return their mattresses. And so that value goes with the profit of $585. So we'll put 0.88 under $585. So to find what we expect the company to profit for one mattress, we're going to multiply the x's times the p's, and then we will find the sum of those things. So that is, we will multiply negative $114 times 0.12, and we will add that, that's finding the sum, that's what we use that sigma symbol for. We will add that to $585 times 0.88. And what we get when we when we multiply and then add those together is we get $501 and $1.12. So that is the expected profit for every mattress that this company sells. So if this scenario seems familiar, it's because there are lots of these companies online that sell these mattresses, and they don't actually cost that much to make. So they will happily ship one to you, and if you don't like it, they typically just have you donate it, or they'll send someone to come get it to donate it, because they sell enough of them and enough people don't return them. It's not even worth it for them to get the mattress back from you. But the company knows this. The company knows the return rate, and so they can figure out how much profit they will make per mattress. And this is true for anything that you get a free trial for. So Netflix or Amazon Prime or any sort of meal delivery service or just any of those services that offer free trials. All of those companies know what the expected value is. They don't know what each customer is going to do, but they know in the long run what will happen. And that's because they've calculated the probabilities and how much money they'll spend and how much money they'll lose or gain. So anyway, expected value is a very, very relevant topic because it is actually used quite a bit. So anyway, the basic formula is we find the sum of the x's times the p's. And we're actually going to be doing this for the rest of the course. So you'll see expected value in our next unit on finance. You will see expected value in our fourth unit when we talk about game theory. So expected value is something that's going to come up again and again. So let's look at another example. All right, so in this example, we have a raffle with the following prizes. First place is $2,000, and there is one winner of that prize. Second place there is $600, and there are two winners of that prize. And then third place is $20, and there are 20 winners. So there are 10,000 tickets that are sold for $1 each, and we want to know what is the expected return for one ticket. All right, so let's once again set up our expected value table. All right, so we'll have our x's and our p's. So the x's will be all of the different outcomes. Now, first place prize, that person will win $2,000. Well, actually, they'll be paid $2,000. However, they bought a $1 ticket. So their profit here isn't actually $2,000. Their profit is actually $1,999. Because they paid $1 to get $2,000. So our x's are always going to be our profits in these cases. So you want to be careful here. All right, so then let's find its probability. So there's only one winner of the first place prize out of the 10,000 tickets that are sold. So that's 1 out of 10,000. So that's our probability. All right, then we have second place, that's $600, but again, they paid $1 to play the raffle, so they would have won $599. There are two winners of that prize, so that's 2 out of 10,000 for the probability. All right, third place prize is $20, so they would win $19 because they, again, paid $1 for the ticket. And there are 20 winners, so that's 20 out of the 10,000. Now, it might seem like that's every possibility, because those are the 3 possibilities that are listed. But of course, that is not everyone. That's 23 people. One person who wins first place prize, 2 people who win second place, and 20 people who win third place. But that neglects everyone else who is going to lose their dollar. So there's the one last outcome, the most likely outcome, is -1. And that is that someone will buy a ticket and not actually win any prize. So the probability of that happening would be everyone else. So if there are 23 people that win prizes, all the remaining people out of the 10,000 do not. So that's 9,977 people out of the 10,000. They don't win anything. They lose their dollar. All right, so now we have our table set up. We have every possible outcome for X. So either you could not win, You could get third place, or you could get second place, or you could get first place. But those are the only 4 outcomes in this raffle. So now what we want to do is we want to multiply each x times each p. So 1,999 times 1 out of 10,000, that's 0.1999, plus, because again, we're going to find the sum of all the x's times the p's. 599 times 2 over 10,000, that's 0.1198, plus 19 times 20 over 10,000, that's 0.038, plus negative 1 times 9,977 out of 10,000, that's negative 0.9977, and that equals negative 64 cents. So what that says is that if you bought that for every ticket you buy, you are expecting to lose 64 cents. Not everyone will lose 64 cents. In fact, no one will lose exactly 64 cents if they only buy 1 ticket. But that is the average loss across all 10,000 tickets. So again, what we do is we just take our x's and multiply them times our p's and then add them all together. All right, let's look at another example. So in this example, 3 marbles are drawn without replacement from a box containing 2 green and 6 orange marbles. What is the expected number of orange marbles drawn? All right, so let's once again set up our expected value table. All right, so we'll have our x's and our p's. All right, so we're drawing three marbles, and we want to know the expected number of orange marbles drawn. So the outcomes are there could be 3 orange marbles drawn, or 2, or 1, or 0. So those are the only outcomes. And so often we'll need to think up what these outcomes are. So if there are 3 marbles that are being drawn, all of them could be orange, or all of them but 1, or all of them but 2, or none of them. And so that's every possible outcome. Now, to find the probabilities, notice what we're doing is we are selecting a group of items from a larger group of items where order is not important. And so when that is the case, that means we use combinations. So we learned about those a couple videos ago. So each of these is going to require combinations. All right, so drawing 3 orange marbles. So as a reminder, x is going to be the number of orange marbles, because that's what we're looking for. We're looking for the expected number of orange marbles. So x will be the number of orange marbles. So when we have the 3 written there, that is 3 orange marbles. All right, so our denominator would be the totals. So that'd be combination. There are 8 marbles total, 2 green, 6 orange. And we are selecting 3 of them. Our numerator is, in this case, we want 3 orange marbles. So that is out of the 6 orange marbles, we want 3 of them. So that's combination 6, 3. And out of the 2 green marbles, we want none of those. So that would be combination 2, 0. Now we could leave that second part off, but you'll see why I'm keeping it on there here in just a minute. So that would be the probability that we select 3 orange marbles given this situation. All right, now let's do 2 orange marbles. Going to look very similar. Our denominator still combination 8, 3. We still have 8 marbles total, and we're still drawing 3. All right, the numerator. So now we want 2 orange marbles. So out of the 6 orange, we want to select 2 of them. So then how many green would that make? Well, if we want 2 orange and we're drawing 3 total, that would mean out of the 2 green, we would want 1 of those. So that's combination 6, 2 times combination 2, 1. So you can see where that 2 went. The 3 from 3 orange marbles went right there in that combination. The 3 and 6, combination 6, 3. So what you might have noticed so far is that a lot of these combinations is the same. So the 6 stays the same, the 2 stays the same, and then the combination 8-3, that stayed the same. Notice the only things that changed here were the 3 and the 0 and the 2 and the 1. And that's because the number of orange and green marbles doesn't change. We always have 6 orange marbles. We always have 2 green marbles. We always have 8 total, and we're always selecting 3. So the things that change is just the breakdown of those 3 marbles, how many are green, how many are orange. So that's the only thing that's going to change between all of these combinations. All right, so then 1 orange marble, combination 8-3 in our denominator again, combination 6 something times combination 2 something in our numerator, because again, all of those things stay the same. The only thing that's changing is how many orange marbles we want. In this case, we want 1. And if we have 1 orange, that means 2 green. All right. Now, finally, we have 0. And you might have noticed something a little different about 0, but we'll go ahead and write it out. Combination 8-3 in the denominator, combination 6 something times combination 2 something in the numerator. So in this case, we want 0 orange marbles, which would mean we would need 3 green marbles out of the 2 that there are. Now, if you calculate that combination 2-3, you're going to get 0 because it's impossible to choose 3 objects from 2 objects. So that entire probability is going to be 0. All right, so now we have all of these. So let's go ahead and do the math. So 3 times the probability for drawing 3 orange marbles. So that's 3 times, and if you calculate all those combinations, that's 20/56 plus 2 times, so again, what we're doing is we're multiplying each x times each probability. Right, so the probability of drawing 2 orange marbles is 30 out of 56. 30 out of 56. Plus 1 times those combinations would give us 6 out of 56. Plus, and then 0 times 0. So that one's, of course, just 0. And so what we end up with is 2.25 orange marbles. So if we drew 3 marbles from 8 marbles, where 2 were green and 6 were orange, we would expect 2.25 of them to be orange. Now, we can actually do this a lot easier. This seems like a lot of work, and it is. There's actually a much easier way to do this. And that is in situations like this where we would use combinations. This is actually what's called a binomial problem. We're actually going to talk about the binomial distribution a little later on. But we can find the expected value of a binomial distribution quite a bit easier in the exact same way that we did at the very beginning. So when I asked if we flipped a coin 1,000 times, how many heads would we expect? All I did there was I did 1,000 times 0.5. And rolling a die 600 times, how many 3s do we expect? I just multiplied 600 times 1/6. We can actually do the exact same thing here. We're drawing 3 marbles, and the probability that any one marble is orange is 6 out of 8, because there are 6 orange marbles and there are 8 total. So if we take the 3 marbles we're drawing and multiply that times 6/8, we get 2.25. So if we just multiply the number of things that are being selected times the probability of any of one of those, then we get the expected value. So now, why did I go through all of that if there's a shortcut? Well, these problems are good practice for finding lots of probabilities. So when you look at the homework, you'll find that these probabilities are separate questions. And so you're going to have to know how to find these each of these probabilities, because this down here, 3 times 6/8, that'll give you the final answer. But if there are 5 answer blanks, and that quick formula only gives you one of them, that doesn't really help you solve the rest of the problem. So anyway, you can use that to double check your answer, and that's what I would recommend doing, but you'll need to know how to find the probabilities as well. All right, let's look at one more example. All right, for this example, the expected value of a game is $200. It costs $200 to play, and if you win, you receive $100,000. We want to know, what is the probability of winning? So this problem is a little bit backwards of what we're used to. So far in this unit, or in this section, we've known the probability of winning, or we've been able to find it, and we use that to find the expected value. In this problem, we're going to use the expected value to find the probability of winning. All right, so just as a reminder, the expected value of x, e of x, is equal to the sum of the x's times the p's. All right, so let's go ahead and write our x's and p's. All right, so if you win, you get $100,000, but it costs you $200 to play the game. So you don't actually win all $100,000. Really, you win $99,800. So that's how much you would profit from this game. Now, we don't know the probability that that happens, but that is the probability of winning, and that's the probability that we're looking for. So let's call it P1. So that is the first probability, the probability that we are looking for. Now, the other outcome of the game is that you lose. And if you lose, then you don't get the $200 back that you paid to play the game. So that would be negative $200. That's our other x value. The probability of that happening, well, we don't know that either. But we know that one of these two things has to happen. Either you win or you lose. And so if we knew the probability of winning was, let's say, 20%, that would tell us the probability of losing is 80%, because we know the two of those added together have to give us 100%. So if we called that P2, we would know that P1 plus P2 equals 1, or 100%. So what we could do is solve for P2 in terms of P1. So we subtract P1 from both sides. So we get 1 minus P1. So we're going to refer to this as 1 minus P1 rather than using a different variable name. So that'll make it easier on us. Now, you're going to see this a lot once we get to game theory. So that's one of the reasons why we're working a problem like this right now, is when we get to game theory, what we're going to be doing is, game theory is all about choosing different options based on having the opposite goals of a competitor. And so basically what we do is we try to make decisions that will enable us to win as best as possible. Not necessarily win, but to achieve the best outcome possible. And we do that by solving for which probabilities we should choose different options. And we do that using expected value. So anyway, we'll talk much more about that a little bit later on, but just know it's coming up. All right. So when we multiply our x's times our p's here, we're going to get 99,800 P1 plus negative 200 times 1 minus P1. Now, that is the sum of the x's times the p's. That's this part of our formula right there. And that equals the expected value, right? Well, the expected value is actually given in our problem. It is $200. So we know this equals 200. So now it just becomes an algebra problem. Now we're just solving for P1. So we can distribute that negative 200. So we'll have 99,800 P1 minus 200 plus 200 P1 equals 200. If we add our like terms, we would get 100,000 P1 minus 200. So our like terms were 99,800 P1 and 200 P1. So we get 100,000 P1 minus 200 equals 200. So we'll add 200 to both sides, and that will give us 100,000 P1 equals 400. From there, we just divide by 100,000, and we'll get the P1 equals 0.004. So what that tells us is that the probability of winning this game is actually very, very small. That's 4 1,000ths. So it's not very high. But the expected value of the game is 200, which means that every time you play the game, you expect to win $200. But the thing about this game is you're going to have to play the game probably a lot of times, because your probability of winning is only 4 out of 1,000. You're going to have to play it a lot of times before you win. So it's a great game if you have really deep pockets, but otherwise probably a not very good game, because you're probably not going to win for a while. But anyway, we've solved for P1, and that is our probability of winning. Again, we defined that to be the probability of winning because we chose that to be the probability under the winning amount of money. All right. Well, that's it for expected value. I'll see you next time.